All right, so this is part two of the various concepts in petroleum engineering. Um, so let's recap on what we talked about in part one. We had a minor introduction into petroleum and hydrocarbons, the what, where, why, and why is it relevant and important to still study. We talked about theoretical concepts and properties of petrophysics, which is the rock properties and the reservoir fluid properties. And then we dove into the life cycle of a well, where we started out with the exploration, and after exploration and identifying prospects, we talked about drilling and the different components and the different subfields that apply to drilling engineering. And then we moved on to logging and what kind of data is acquired with wireline logs or MWD tools and etc. And then we talked about completions and how a completion engineer is utilized throughout the life cycle of a well after certain steps have taken place. And then we explained production engineering and reservoir engineering, which have more of this holistic, collective insight or application in the sense that it's not just one well that they're looking at, they're sort of looking at the entire field or the entire project as a whole and trying to maximize production through there. And that led into the final topic of part one, which was petroleum economics, what consists of the financial aspects to a petroleum project, and all the different attributes that are associated with that, such as the income, how the rate of return is calculated, productivity index, and capital expenditure or operational expenditure. So moving on to the second part of today's lecture, it will be more mathematical, and the idea is to cover sort of the introductory level mathematics and physics concepts that apply or are used quite frequently in petroleum engineering, and then we'll take the mathematical concepts or the basic level concepts of physics or fundamental laws that we use and move on to how they apply to flow equations. So I've just sort of selected a few flow equations that are considered important, and I'm really interested, or I really enjoyed petrophysics and the concepts of how fluids flow through porous mediums. So that is the subject that I chose. So we'll start with the mathematical concepts. These are things that you should be familiar with, and if not, we'll kind of go in a very high level and basic steps so we can become more familiar with them, so then we can derive the fluid equations more easily. So the main concepts or the topics that we will cover today with respect to mathematics is differentiation, integration, and then different matrix operators and linear algebra, because essentially when it comes to deriving equations, whether it's flow or drilling or even simulations and using numerical methods, you are essentially doing a lot of partial derivatives and 3D integrations or volume-like integrations, right? So, and when we say 3D or when we're using multiple parameters for optimization, we're really working with matrices, Jacobian matrices, and etc. Starting with differentiation. So differentiation tells us how a quantity changes with respect to another. In petroleum engineering, pressure changes with respect to distance, fluid velocity changes with respect to location, and temperature varies in space. So we extend differentiation from this one-dimensional like derivatives to partial derivatives on a two-dimensional plane or a three-dimensional plane, which give us gradients, which is another word for derivatives or differentiation, and directional rates of change, right? This is extremely important. And these derivatives become the building blocks for fluid flow equations. So here we focus on the most basic derivative definition as the limit. So you can see that displayed on the slide. Um, and this is important because flow equations like Darcy's law depend on pressure gradients, which we discussed earlier, and they are basically the first derivatives. So when we say something like pressure drops along a given x or a given distance, we mean dp dx, which is kind of like what you're seeing here with the delta f with respect to delta x or delta f with respect to delta y, right? And understanding this basic concept is really essential to understanding how to apply it to higher dimensions, right? So when you're looking at the 3D world and so forth, or a more real-life example. And in multi-dimensional reservoirs, pressure is not just a function of just x, but in reality, it's a function across a 3D plane. So it's of x, y, and z. When we're talking vectors, right, you describe a 3D vector or a vector through an actual realistic space is three-dimensional, right? So then the partial derivatives become delta p with respect to delta x, and then that's in one direction, but you want to calculate in all three directions to understand where your vector is actually going, and this becomes extremely crucial for modeling radial, spherical, or irregular flow geometries, right? So when we're looking at the diagram here in the slide, this is the most basic function, right? And this is kind of a discovery that, two physicists, you can say, were working on calculus at the same time. There was Newton, Isaac Newton, who was an English physicist, and you had Leibniz, who was also a German physicist, and they were sort of figuring out calculus roughly around the same time. But they were trying to explain movement through mathematical derivation, right? So in its most basic form, you can say that you're just calculating an incremental change as you approach zero. So you continue to approach this infinitesimally small point, and at that moment in time, that tangent will tell you the delta or the slope. And that sort of is explaining how things are moving with respect to one another, right? And when you do this on a 1D plane, you can see in the most basic form displayed in the graph above here. But obviously, as you increase or go to 3D, which were the dimensions or the plane dimensions that we live in, you want to do it vector-based. So then there's vector-based differentiation, and that's basically where you take the partial differentiation with respect to each variable. So given a single equation or a single function, you would have x variables, y variables, z variables, and you want to take the derivative of each one with respect to itself, and then that will sort of give you the gradient, right, on a vector-based plane. So when we're talking about this, we can sort of introduce the topic, the vector operators, right? Because now we can talk about, with respect to petroleum, you have your flow equations, gradients, divergence, and the Laplacian equation become extremely important, right? Where the gradient will measure the steepness of pressure, and the divergence can be used to measure how much fluid spreads out or collects. So this goes back to that fluid movement and expansion or compressibility. And then the Laplacian can combine the second derivatives and appear. It appears in the diffusivity equation, which is extremely important when you're trying to understand the operators or the derivation of a 3D flow. So it's used quite frequently in respect to modeling, right? So, and we can't really talk about differentiation without talking about integration, right? And integration is a really interesting concept. At the most basic level, if you're integrating from one point to the other, you're kind of trying to calculate. Mathematically, it's telling you the relationship basically from 2 points is the area. So on a given xy plane, you have 2 points, and you integrate from point A to point B. you would find the area under that line or that given shape, right? And integration is computes accumulation. There's lots of numerical methods that are used for doing this integration. And whether it's mass, pore volume, fluid flux, or energy, the fundamental theorem behind all of this is connecting derivatives and integrals and letting us move between the local change and total accumulation for a given variable or a given function, right? So in one dimension, on a one-dimensional plane, we can think of the integration, as I mentioned, as the area under a curve or a given shape or a given line. And we can see this in oil and gas or petroleum engineering concepts such as the pressure distribution across a given reservoir section, right? So on the one-dimensional concept, you can think of pressure, right? And then differentiation and integration are basically inverse operations. So if you take the integral of one function and then the output of that, you take the differentiation or the derivative of that output, you will return back to your initial function. So with that intuition, we can say that this shows that the integration accumulates the area under the curve and differentiation retrieves to the original function, right? So when we want to look at this, I guess on a very high level, if we take this as a proof, we're extending the concept of the area of the one-dimensional, and then so if we integrate again, we're going to the volume, right? And that sort of makes sense, is that we go from line, and if you integrate, for example, some, let's say, some equation with no variables, you get this line. You integrate the line across a function, you will get the area, and you integrate that area, you will get the volume, right? And that's depicted by the triple integral sums for a given infinitesimally small volume, right? So in 2D and 3D, we can think of terms of 3D when we're talking about this, right? Is that we can compute as an application in the reservoir world the given reservoir blocks that we're looking at, right? So for a given specified scope, we can calculate certain things about the nature of that reservoir or the movement of that flow by using these triple integrals or three-dimensional integration, right? And understanding coordinate transformations, whether it's Cartesian, cylindrical, or spherical, is extremely critical and crucial when you're trying to understand or explain the radial flow or the radial well flow and aquifer modeling or any type of fluid-like modeling, right? So with this in mind is that we can see that here on the slide, right, is that on the top equation you have this integral from f of x dx, which kind of becomes this capital F of B minus capital F of A, which is essentially just saying the area, right? And you can go back and forth between f of x and capital F of x simply by integrating or taking the derivative. And on the three-dimensional plane, when we're thinking three dimensions, we're thinking vectors, and the reason why we think in terms of vectors is that it allows us to think in terms of matrices, and it allows us to really understand how things are moving in the real world, right? And again, similar to differentiation, and when you're taking the integral, that dv or the d volume, right, is that you can write that in terms of dx, dy, dz, right? So it's with respect to each individual parameter for a given vector. And once we become familiar with the integration and the differentiation concepts, we can really start getting into these mathematical concepts that are associated with physics. So something like the divergence theorem, which basically connects a surface integral to a volume integral, right? And if you look at the left side here, it's the surface integral of the vector field F over a closed surface S, and on the right side we have the volume integral of the divergence of F over the region V enclosed by S. So it's the sort of the total outward flux of a vector field through a closed surface, which is equated to the sum of all sources inside the volume. Now, the theorem is essentially the mathematical bridge that transforms integral conservation laws into differential form of partial differential equations, right? And when we're talking about fluids, where all of it boils down to is that this is a change in energy, right? When you're displacing the pressure, movement of fluid, right? All of this is one big energy equation, you can think of it. And the divergence theorem behaves as that bridge. So another important concept is the Reynolds transport theorem. So let's go down the slide. So this is for a given property f of x and t in a moving control volume omega of t. We can write this equation and we'll go through. So just a heads up, for each given equation, what we're going to do is basically define the equation, define the variables, and then we're going to make our assumptions and go through either the theorem or the proof or the rationale behind the equation, right? So that's just something to keep in mind when we're talking about the flow equations. But with respect to this concept here, you have this equation d of dt, the integral of omega with respect to t for a given f dv, and you can expand that equation to what's shown on the slide here, right? Where omega of t is the time-dependent region, so it's your controlled volume. The differentiation or delta of omega of t is your boundary surface. V is the velocity of a fluid at a given boundary. And n is your outward normalized vector. And dv and dA are basically the volume and surface elements. So we want to break down this equation, but this is the foundation of all conservation equations when it comes to engineering. So this is a very important concept. And on the left side here, what we're actually saying is this is the time rate of change of the property inside the moving volume. And the first term on the right-hand side is this local unsteady change inside the volume. And that second term is the flux or the net flux of the property across the given boundary. So this theorem converts system-based conservation laws, so you can think as the Lagrangian view, into a control volume form. So you're moving to a different view called the Eulerian view, which is essential in fluid mechanics and thermodynamics, which also ties back obviously into flow equations that you see quite frequently in petroleum engineering, since these are the laws that govern how we create our equations and how we use them. So the Reynolds transport theorem basically states that the total accumulation is equal to the local time change plus the net flux across boundaries. So when we're thinking about linear algebra, it's basically the application of what we've learned across matrices or big systems, right? So reservoir simulators are these humongous large systems containing linear equations, and each grid block becomes an equation involving pressures in neighboring cells, and each block sort of affects the other one, and you want to be able to calculate each block at a given point of time. And when you're talking about these blocks for simulations or so forth, or modeling, you're basically talking about matrices, right? So you must really understand the fundamentals of matrices and how you can solve something numerically from that forms the core or the backbone to that simulation. So to basically understand your reservoir, you must understand how you're modeling or what that modeling is doing. And to understand that, you really need to have a strong grasp of linear algebra, right? So this will be like a very basic 101 kind of run through on some linear algebra concepts or matrices. But you have like matrix multiplication, for example, it corresponds to this chaining linear of operations. And you must first validate the shape size or size of the matrix. So in this simple example, you have both matrix A, which is the 1, 2, 3, 4, and B is 5, 6, 7, 8. So this is a very basic example. That means that we expect our matrix C to come out 2 by 2 as well. And the shape is defined by whatever is being multiplied, right? So we can go through this example. So just to validate, so the way you multiply when it's respect to matrix is that given the two matrices, you want to sum the values of the products at the given location. So, and you kind of go across and then down, across and then down, across and then down. So you can see here for C11 is that you're taking A11 and B11 and you're adding it to A21 and multiplying it by B12, right? So this concept of going across and then down, and you continue to do so to get all your elements of your output matrix C, and you can validate the math or go through the example if you like. It's relatively simple, and you would find that C11 would be 1 times 5 plus 2 times 7, which is equal to 19. C12 is 6 plus 16, which equals to 22. C21 becomes 15 plus 28, which is equal to 43. And finally, in our last element of our C matrix, we have C22, which is equal to 18 plus 32, which is equal to 50, giving us a output matrix of 19, 22, 43, and 50, right? And this is relatively important when it comes to petroleum engineering, especially in reservoir simulation, permeability effects, transmissibility, pressure interaction between blocks, as we mentioned, encoded in like a matrix product. And it's really important to emphasize that this is really where this row by column multiplication becomes where partial differential equations come from, right? And how you approach all these partial differential equations. Other matrix characteristics that we want to be familiar with is terms like transpose or inverse. You do want to, or in general, when you're working with matrices or you're trying to optimize an equation or you're trying to take all the partial derivatives with respect to some function, you want to be able to manipulate the matrix to make your life easier. And mathematicians and petroleum mathematicians will do this quite a bit to try and simplify the mathematics, right? So when we say that we're transposing, the idea is that you're switching the rows and columns, right? So you're kind of you're switching a matrix from, so whatever is considered a row coordinate or a row value, you'll switch it for it to be a column value. And this is really important when it comes to symmetric permeability tensors and numerical stability. So again, this goes back to that modeling, right? And then when you take the inverse, there's a whole proof for the inverse of a matrix that you can find online. But this is where a matrix is non-singular and solving a linear system is conceptually equivalent to multiplying it by the inverse. So this concept is the backbone of how you can use or improve the speed on your numerical techniques when it comes to simulations and modeling. One thing to note that, like we mentioned in part one, is that these simulations and these models take a relatively really long time, right? So when you're trying to do the math, you're trying to think of ways to create your models and your simulations to be as optimal as possible while maintaining the data integrity or the output integrity. So you want to remain as accurate as possible, but also with the objective of speeding things up, right? So then bringing this all together from the mathematical concepts, as you can see this example below, but basically is that you can use the calculus and differentiation, and that's basically what partial differential equations are talking about, is that you can use them for on the matrix level, and when you're using them on the matrix level, it allows you to talk in terms of vectors or in terms of the three-dimensional plane, but also use, multiple parameters, right? So this is where optimization comes to play, this is where numerical methods come into play, and matrix calculus is just, you're basically just involving the vectors, and the matrices become defined as functions, right? So when you're talking about gradients or divergence or vector fields, differentiation rules extend naturally, and you can kind of scale it as many parameters as you would like or need to use. And this really becomes the backbone of how to express fluid flows or fluid flow models more compactly, right? Because you can sort of represent this for a given. You can see here that for one partial y with respect to partial x, you can write this and expand this as much as you like for computing or the computational aspect to it, but you can kind of also mathematically give a representation in a more compact method and really start to create models in a readable or accessible way, right? So that's something to keep in mind. And with all this concepts in math is that we have to kind of sort of note the two backbones equations, and this is more on the physics side, but we want to be able to define these as well, because when we're going through the derivations, obviously not all of them will be a step-by-step derivation. So we want to just understanding this fundamental concept, right, is that we can use this intuitively when we're looking at our flow of media. Because when we say conservation of mass, this sort of applies to almost everything in the world, right? So if we're using the Reynolds transport theorem and the divergence theorem, we can just derive this equation where we have partial rho with respect to partial t plus the gradient of rho mu, and we can set that equal to 0. And what that's saying is basically that this fundamental equation, that mass cannot be created nor destroyed, so it's always being transferred from one state to the other or from one entity to the other, but it is never created nor destroyed. And it's sort of this is sort of from a physics perspective, the starting point for deriving the diffusivity equation and the continuity equation in petroleum engineering, right? And what you can see from this, because if you're talking about conservation of mass, that you're basically the conservation of the fluid, how it changes from one state to the other is one thing, but that allows us to really understand how things are behaving from a mathematical perspective and a physics perspective when it comes to fluid analysis, right? And if we talk about conservation of mass, these are always put together, so I just wanted to include them. But it's the conservation of energy, right? And with these two fundamental things, we can sort of define a lot of things about our reservoir and how our fluid is flowing. So we can derive the conservation of energy, which includes the internal energy, the heat flux, and the work done by the delta pressure, right, or the different pressure forces. And you can see the equation here where it's including or rewriting kind of the conservation of mass with respect to the energy, right? And on the most highest level, you can think of this as you're just combining the two different categories of energy, right? Is that you have a potential energy and an actual energy, or a kinetic energy, or whatever, a thermal energy, and the summation of those must always equal the same, right? They must never change, because at the end of the day, at any given state, is similar to the mass law, is that we can say the same about energy, is that energy cannot be created nor destroyed. And this becomes very important when you're talking about thermal recovery modeling, or you're looking at steam floods or water flooding. And these are things that we've seen a lot, right, in the part 1 and what petroleum engineers work with. So as a conclusion, before we move into the fluid flow equations, just to summarize, is that we are sort of defining or setting up the stage for how we can approach these petroleum engineering equations that we're about to look at, and they're all relative with respect to flow, right? So we've covered the multidimensional differentiation, we've taken the integration and differentiation from 1D to 3D, and we see how we can apply that in linear algebra and matrices, and then also taking these mathematical concepts and combining it with some physics laws, some very basic or critical physics laws that are very at the top level. And these mathematical concepts put together are kind of the backbone required to derive the petroleum engineering flow equations that we're about to see. And they also prepare you for more advanced derivations, such as Darcy's law, pressure diffusion, the Buckley-Leverett, and PVT-based material balance models, right? And we'll go through some of these today in today's lecture. But yeah, you're going to need these concepts throughout your entire degree and most likely throughout your entire career if you're going to work in the oil and gas industry field as a petroleum engineer. So with that in mind, so we're going to be talking about a few fluid flow equations. So taking the mathematical concepts and the physics concepts and trying to apply them and to understand the derivations or the rationale behind equations that we see in reservoir engineering or in petrophysics when we're trying to understand the change in pressure or change in flow, or with respect to our well, we're trying to understand the integrity of our well, was our artificial lift job successful, etc. So we're going to start this off again with one of the most important equations in petroleum engineering in its most simplest form, which is Darcy's law, and we'll apply the assumptions for there. So for every single equation that you see here, or for every single topic, what we'll do is that we'll explain from a high level what that equation is doing or trying to measure or trying to accomplish, and then we'll display the equation, and then any variables that haven't been displayed or explained before will be explained. And then we'll move from there to the assumptions that equation or that derivation is making, and then sort of explain the rationale or the derivation itself for that given equation. So we're going to try or attempt to explain how that equation was arrived at, right? So we'll start off with Darcy's law in its most simplest form, and then we'll move on to taking Darcy's law and making it radial, and that will allow us to understand how things are behaving with respect to a well. So lots of these equations you'll see sort of the simplest form of it. Then we'll take it to a radial form where we're looking at a reservoir going into a well, but we'll assume that it's a single phase or a homogeneous structure or fluid, and then we'll try and add this layer of complexity as we go. So we'll move from Darcy to radial Darcy flow, and then we'll explain what the diffusivity equation was or is after taking sort of those concepts we saw in the previous slides, and then we'll take that equation and turn it into the radial diffusivity equation. And after that, we'll go into the line source solution and see how that helps us understand pressure transient and well testing analysis. And then we'll take a look at the infinite acting radial flow equation, or the IARF. And after that, we're going to add a element of reality to our equations with the skin factor, which is will sort of tell us more about how well or how good our conditions are at the well level. So it will tell us more about the well integrity. And after that, we'll define the productivity index, which has multiple applications and is used across the entire life cycle of a well, especially in the secondary and tertiary phases when you're trying to improve the production. And then we'll go into the Vogel inflow performance, and see how that's applied. And then finally, we'll come back to Darcy, but in the form of multi-phase flow, which sort of is, again, a more realistic depiction on how we can use Darcy with respect to when there are multiple permeabilities present or there are multiple fluids present. And after that, we're going to take a look at the Navier-Stokes equation, which is extremely important, and then we'll move on to the Leverett equation, and then finally we will show the solution to the Buckley-Leverett equation. Let's get started. So starting with Darcy's law, right? So Darcy's law, again, is the fundamental constitutive relation for single-phase flow in a porous medium. It basically is linking the pressure gradient to a volumetric flow, and it introduces this variable that tells us, or a property of the fluid, which is permeability, right? And this it's the combination of the rock and fluid, and it's the ability to the movement of that fluid, right? So we're trying to describe how well can a given fluid move through a given porous medium, right? And it's the backbone, honestly, to reservoir engineering, but it's also the backbone to lots of the petrophysics concepts and lots of the things that are acquired via wireline. Is telling us about this permeability. So no matter what field you go into in respect to petroleum engineering, if you're working in the field, you need to be familiar with terms like permeability and porosity, how to calculate them, and really understand the fundamental physics behind it, right? So let us define the equation again here. It's reordered from the first slide, but we're basically solving for Q, which is your volumetric flow rate, and it's equal to negative K, which is your permeability, multiplied by the area, divided by the viscosity, and all of that is multiplied by this pressure gradient, right, which is this delta P over a given delta X, similar to how we describe dy dx in the mathematical slides, right? So let's talk about each variable and what units. The units honestly don't matter as much, but the more important thing to note is the dimensions, right? So volumetric flow rate is some volume over time through a given area A, which is area, so length squared, and then you have permeability, which is Darcy's or millidarcy's, and you have the fluid viscosity, which is some pressure times time, and pressure is obviously, so pascals, you can think of it as pressure, which is some force over area. And if you do this, and the x is some distance, right? And if you put all the dimensions together, you will find out that they will all cancel out to where you know what your dimensions of Darcy is, right? So you can do that as an exercise to understand the dimension nature of a permeability. So some of the assumptions made on this very basic equation, or this basic form of the Darcy's equation, is that we're making the assumption that this is a laminar flow through a given pore network or some pore medium. So you can think of it as it has a very low Reynolds number, it is homogeneous, it is isotropic, and it's a single phase incompressible flow, right? So when we're talking about this, obviously in the oil and gas world, this does not exist, essentially. First of all, most of your fluids are heterogeneous, and even if they're homogeneous to some sort of respect, they would not be laminar, right? Oil is actually this, or how oil moves is very, it's not a Newtonian fluid, right? So it behaves a bit differently, but that's for a different topic, right? But when we're trying to understand the derivation of the Darcy's law, we can start from basically what we talked about in the part one, which is that Henry Darcy was a physicist and he was able to observe the he worked in water irrigation systems, right? And he was trying to optimize or understand how water would flow through some irrigation pipe that had some sand or mud in it, right? And his observations were that the flow rate is proportional to the pressure difference, or the delta P, and it's inversely proportional to the length and viscosity. So if we can write these mathematically, is that we can say that Q is proportional to the pressure gradient, and we can introduce this variable K to make the equality, right, is negative Ka over mu for the given pressure gradient. One thing to note is the negative sign, and that's just the nature or the direction of the pressure, right? So you're trying to formulate this or use this in a real life example, or take this to a more accurate depiction of what's happening, right? And when we're moving from reservoir pressure to the well, or in terms of Henry Darcy's situation, is that we're sort of going in the negative direction, right? So think of that negative as purely as an arbitrary direction decision that was taking place, right? And also one thing to note, or a takeaway we can say, so after each derivation or whatever, we'll kind of have these key takeaway points that we want to discuss. Darcy's law is basically explaining to us what the mobility of a given fluid is, and that mobility value, you can think of it as K over mu. And this is sort of the basis for the diffusivity and the material balance equations, right? And we'll talk about the diffusivity equation after we explain how to apply Darcy's law on a radial front, right? Sorry. Okay, so the radial Darcy flow, as we mentioned, it is natural to, when you want to describe things in the oil and gas world, you want to describe them radially, right? Because when we produce our oil or produce our hydrocarbons, we're producing them radially with respect to the reservoir into the well. So what this formula gives us, and you can go through the math, basically you instead of dp dx, you're doing dp dr, and for the given area, if you have the given area of the sphere, and then you move the equation around and you kind of integrate it, and we'll go through those steps in a second. But what this formula allows us to do is to give a steady state rate pressure relation from the flow from the reservoir into the well, and that's connecting measurable pressure to permeability and flow. So again, the objective or the name of the game is to explain the delta P for some given area or surface area, right? So let's go through this equation. Is that we have Q equals 2 multiplied by pi multiplied by some height, which is what's different from the basic Darcy law equation for a given pressure, but now here we can actually define what those two pressure points are, and we can say PE is the pressure of the environment or the pressure of the well, subtracted by, and you subtract the pressure of the well, which is PW, and you have mu multiplied by the ln, or natural log of RE over RW, right? So again, the dimensions will check out the same, but Q is the volumetric flow rate, K is the formation permeability, H is the reservoir thickness, and PE is the pressure at the external boundary, but in a way we can just say that that's the reservoir pressure at that given time or at that given scope. PW is the pressure at the well bore, so the pressure at the point of where the fluid is flowing into. And then we can say the same for RE and RW, where RE is that reservoir radius or the drainage radius that we're looking at, and RW is the wellbore radius. And finally, mu, again, is the same as before. It is the fluid viscosity, right? So again, this Darcy law is quite interesting because it is sort of a property, or we're trying to understand both the rock and the fluid at a given time, and the output tells us the ability of movement, right? So let's go through the actual derivation. First, we must ensure our assumptions are correct. So again, here, this is sort of a basic form. This is not really what's applied in the real world, but it is the first stepping stone to getting there. We're assuming that this is a steady state flow, so there is no impediments or something like that. There is a radial symmetry, and it's single phase and incompressible. So we're still sticking to this single phase concept, incompressible, so we haven't introduced basically different phases, right? So we haven't introduced water, gas, and oil. We're just looking at one fluid. And we're assuming that for the given depths that we're looking at a homogeneous formation rock, which is also generally not the case when you're looking at the real world. But the way we're describing it is that you can start off with basically the way we derive this is you replace the area of equation with basically the surface area of a cylinder, right? And that cylinder with the surface area, and then you replace the pressure gradient with respect to the radius, right? So 2 pi RH becomes your area equation. And when you do this, you can kind of rearrange the dP and the dr. So if you look at here, is that you want to push the dP on the left side of the equation and keep the dr on the right side of the equation, just because it allows you to integrate easier and it just makes the math easy. So we're left with this pressure gradient integration on the left for the left side of the equation, and on the right we can sort of take out all the things that we're assuming constant, since we're going to be integrating with respect to r. And for those of you who are not familiar with this mathematical concept, but when you have 1 over r dr or dr over r, that's just basically it becomes the ln. When you take that integral, it becomes the ln of the two values over each other, right? And the natural log also is that if you're dividing in a given, natural log is the equivalent of subtracting. That's just one of the properties of natural logs, right? So when we take the integrals on both sides, we know the wellbore pressure, we know the given distance or the shape of the reservoir ideally, and we know the pressure of the reservoir, so we can sort of solve for everything, and we finally get that this change in pressure from reservoir to wellbore is equal to this negative mu q divided by the surface area kind of manipulated 2 pi h multiplied the permeability multiplied by the natural log of RE over RW. But even though that this is a correct form of the equation, we want to kind of write things in terms of flow, right? Because flow is the value that we can measure when we're doing this. So for a given volumetric flow rate, we can sort of solve for the other variables with our known givens, right? And you finally get this equation that we saw initially, where it's this volumetric flow and this area has been sort of replaced by this 2 pi h, and you have your permeability, the delta p, and now instead of a delta x, you're seeing this natural log of RE over RW, right? And this becomes the radial flow, and this is extremely important as well because, like I said, this is the first stepping stone on how to really start to do the math to get to the real life examples or the real life application, right? And we can also see this sort of pattern now that if RE over RW is large, then that basically dominates the delta P, right? Due to its nature of the natural log. And this becomes the basis for the productivity index or pressure transient testing or well testing analysis. So this concept is really important to get yourself familiar with, right? So now we've kind of defined Darcy in its most theoretical aspect, but still we gave it some real life application with respect to the radial Darcy flow, because we can sort of see how fluid moves through into a well, right? But in very ideal and non-realistic situations. So it's sort of a naive, idealistic approach, right? But it sort of tells us a lot of how things are behaving, and we can see that the relationship between the different variables and different parameters, similar to part one when we were talking about when you're thinking about oil and gas or fluids, you're thinking about PV equals T, right? So that's sort of what's proportional, what's inversely proportional. This becomes that for the Darcy equation, right? So we'll come back to the Darcy flow equation, but more as the multiphase, but we'll finish with that since it's more complex. So now we'll move to the diffusivity equation. Sorry. So the diffusivity equation, is we're basically moving from steady flow to unsteady flow. And when the pressure, I apologize, when the pressure changes with time, that leads us to the diffusivity equation, the heat equation, and the analog for reservoir flow, right? So let's go through the equation. Here you have some delta P with respect to delta T is equal to K over phi times mu times C, all multiplied by the Laplacian operator, right? So what this means is that it's telling us the pressure that changes over time dependent on the curvature of the pressure field. And it describes how the pressure transience propagates, right? So when we want to define all our variables here is that we have pressure, right? And pressure with respect to time. We're familiar with permeability, viscosity. We're introducing phi, which we've seen earlier, which is porosity. And then the total compressibility. In the previous part of the lecture, we talked about oil compressibility, but here we're looking at the total compressibility, which is including both the fluid and the rock. And like I mentioned, that gradient 2p is kind of this Laplacian operator, which is kind of the sum of the second derivatives, right? So now let's move to the derivation. There are two ingredients here when we're talking about the conservation of mass and Darcy's law, right? So before we get into that derivation, let's define our assumptions. And the assumption is that this is a slightly compressible single-phase fluid, as in it's relatively linear in pressure. It's isothermal conditions, so that means we're assuming constants for these variables, permeability, porosity, viscosity, when in the real world that's not the case, right? These things are kind of varying and oscillating, and it is sort of a valid continuum approximation. So when we want to go through this derivation, right, we start with the mass conservation equation that we just saw in the previous few slides, and we're equating it to zero, right? Because based on the law is that mass cannot be created nor destroyed. And what we're doing is that we're taking Darcy's flow equation but writing it in the form of velocity, and we're taking a slightly compressible fluid that is dependent linearly on pressure, and we're inserting that Darcy's velocity equation into the continuity equation, right? And if you assume that these parameters that we're saying are kind of constant, that they're a very small variation, we can sort of remove that density, right? We can remove it because we can assume that it's a constant, and then we can finally solve for delta P with respect to T, or the pressure gradient with respect to time. And this diffusivity sort of controls how fast pressure is propagating, And given a high permeability or a low viscosity or a low total compressibility will mean that the pressure is stabilizing quickly, right? So this equation is the engine behind well testing and reservoir simulation and PTT or pressure transient analysis or pressure transient testing, right? And one thing to note is that we are given, or we are able to understand kind of, is that we can have this diffusivity value or parameter now that we can write in terms of permeability, viscosity, porosity, and compressibility, right? And this governs the real pressure gradients for things like reservoir simulation, numerical reservoir simulations, or something called Green's function. So it is extremely important, and this is where we're entering the real world of the mathematical applications into our simulations, right, or into our modeling. So since we've talked about the diffusivity equation, we can now enter the radial diffusivity equation, right, which is we can specialize this diffusivity equation to a radial geometry, which allows us to talk about wells. And this simplifies the partial differential equations that we work with, and it allows us to derive this closed form pressure solution, right? So when we look at this equation, we can write the diffusivity equation we just saw, but in terms of radius. And now this alpha parameter is basically accounting for what we just discussed is permeability over the porosity multiplied by viscosity and the total compressibility, right? And the variables we're working with we should be familiar with, right? But I guess the new one is that we're introducing radius, and now we can kind of quantify the collection of permeability, porosity, viscosity, and compressibility into this variable called diffusivity, right? And one thing I advise you to do is, again, always check the dimensions. So go through the equation, go through the dimensions. But for now, what we're going to do is we're first going to go through the derivation, but not go through every step. But we're working with these following assumptions, right? So the assumption is that, again, it's similar to the radial Darcy flow. We're assuming ideal or naive environments, right? So we're assuming a radial symmetry. We're assuming no angular or vertical variations. We're assuming no oscillations. And we're looking at this slightly compressible single phase fluid. And we're working with a lot of constants here. And the reason we're doing that is that it sort of makes the mathematics easy and allows us to gain the intuition of the equation or the derivation and then apply it to more difficult scenarios, so multi-phase, compressible fluids, and so forth, right? So it allows us to scale the complexity quite a bit. So let's go through the derivation, right? So is that we're taking the general diffusivity equation that we just explained, and then we're rewriting it in cylindrical coordinates, and then we're sort of plugging it back in. And that's really the entire derivation. Now, why is this needed, or why does this become really important, is that this equation is describing the transient drawdown around a producing well. So again, it allows us to think of these equations in an application around a well in a reservoir. So it allows us to paint a picture sort of to where it's more applicable to the oil and gas field. And so we can think of it also as that it's needed for the well testing type curves. So that's when it comes to pressure transient testing, when you're looking at log-log plots, when you're looking at semi-log plots. And this sort of stems from all the partial differential equations that you will be looking at as a petroleum engineer. And an interpretation that we can take from this is that the term with the R inside the derivative accounts for the expanding flow area as you move away from the well, right? So the diffusion slows down because the flow continues to spread out, right? And this is sort of the basis for the other equations that we're going to look at, like the line source equation and the well testing and pressure transient analysis that we'll also be covering, right? So moving on, we're going into the line source solution. Sorry. So the line source solution is basically a fundamental solution for an infinite domain with a line or a point in 2D space source, and it's used to model the transient drawdown from a constant rate well in an infinite reservoir. So it is the exact analytical solution to the radial diffusivity equation for an infinite reservoir and a constant rate well starting at time 0. So it becomes really the fundamental or the foundation or the backbone, you can say, for well testing analysis, right? So taking a look at the equation, is we have P with respect to R and T, so the radius and time, and it's basically equal to the initial pressure minus the flow multiplied by the viscosity divided by 4 pi multiplied by the permeability times the height. And then you multiply that entire function by this exponential integral function where you have also multiplied by the negative r squared over 4 multiplied by the diffusivity multiplied by time, right? So it's quite a bit, but let's go through our assumptions and the derivations. So the assumptions is that we have this infinite reservoir. So when we're looking at drainage, right, and reservoir engineering, obviously we sort of have this boundary in real life, and that affects a lot of things about the primary recovery or the drainage of how we can get that hydrocarbons out or all our fluids out. But this is assuming that it's sort of an infinite reservoir. So it's so big that the boundaries don't necessarily affect what we're looking at here or the scope that we're trying to achieve. So also is that another assumption that you're making, and again, this is a very ideal scenario or ideal situation that is not really realistic in the real world, is that you're assuming a constant volumetric flow rate at t equals 0. And then you're also assuming that the well radius is approaching I guess infinitesimally small, so it's approaching 0. And you're still working with this slightly compressibility, and you're taking a lot of the variables that you're working with and assuming that they are constant throughout the entire equation. So when you're trying to derive this, we're not going through all the steps, but we can kind of work through the rationale of it. And sorry, 1 second. This is basically the Green's function solution. So you start with the radial diffusivity, you add a source term representing the well. Mathematically, that's a delta function at r equals 0. And then you're solving something using similarity variables and the integral transforms. And then you finally get this output of this exponential integral form, which is fundamental to 2D diffusion or kernel integrated over time for a given constant rate, right? And you can see that in the equation that the full derivation is much more complex and is using a lot of partial differential equation methods. But the key takeaway of this is that this equation or the function is trying to describe the transient drawdown, right? So it's trying to explain exactly how that is occurring. And one thing that you can take away from this is that for early times, so for a given the first incremental steps of t or at a given small r, that this exponential integration function can be approximated, which gives you a more simple log time solution. And for well testing, we usually want to plot pressure versus log time, And like I mentioned before, that in petroleum engineering, there are a lot of log functions, or a lot of things are plotted on a log chart or a semi-log chart, and that's just because we can see better patterns, or we're able to analyze more. So in this case, for example, we can do that because you would see sort of this linear-like pattern, right? And this is usually used in the application aspect is for matching well test data when you're looking at the early times, right? So now we're moving on to the infinite acting radial flow, most commonly referred to as IARF. And that is a practical approximation of the line source solution at late times, and it's useful for log-log and semi-log analysis of well tests at intermediate and late times, right? So here we're really looking at well test analysis, and this equation is very relevant for that. And it's basically turning this Tay solution into something linear when we plot it on a semi-log plot, right? So let's go through the equation. You have P of R with respect to T again, but now you're sort of, instead of writing this exponential integral form, you have this natural log of 4 alpha T divided by R squared minus this gamma. And this gamma is this Euler, or it's actually called Euler-Marchoni constant, which is roughly close to this value here. But yeah, it is used when you're trying to understand, again, the well testing analysis, or pressure test through pressure test analysis, or pressure transient testing, right? So before we talk about our assumptions, let's first explain why it's needed. It's basically trying to simplify that exponential integral function for large times. Like we just explained, is that exponential integral function does well at early times, so we're just trying to find an equation to explain when a lot of time has passed, right? Which is relative to our flow. So once the pressure transient has propagated sufficiently far enough, this exponential function or integral function that we saw before in the line source solution is that it starts to behave logarithmically. Sorry. So that's why we can rewrite this equation in that sense. So first, let's talk about our assumptions. Our assumption is that a large T such that R squared over 4 alpha T is less than 1. So, and the other assumptions that we're making are the exact same as the line source. So that's the only assumption change that we're making. Now, let's go through the derivation. So we can use the small argument approximation for the integral, or the exponential integral function, and we can sort of say that it's proportional to y plus natural log of x for any given x that's less than or much less than 1, right? And then if we can rewrite this x and set it equal to r squared over 4 alpha t, when t is large, x becomes small, right? So it's inversely proportional. So we can substitute now for the exponential integral function into for x, right? So we can take these, or we can substitute r squared over 4 alpha t into the exponential integral function, which we can say now is y plus natural log of r squared over 4 alpha t. And then when we take that and plug it back into the Tay solution, we can get pressure is equal to the initial pressure minus the volumetric flow rate multiplied by viscosity, all divided by 4 pi permeability multiplied by h. And we can sort of plug our assumption in there. So we can do this gamma plus natural log of r squared plus 4 alpha t, right? And then we can rearrange that equation, and we can finally solve for the IARF. And again, the key takeaway from this, or the key thing to consider, is that this is the basis for semi-log straight line methods, which is also known as Horner type analysis. And you're trying to basically estimate the permeability from the slope that you're getting, right? So this is sort of, we're starting to see here how we can manipulate physics equations or mathematical equations to apply to our reservoir, right? So, and how to apply, and in terms of properties of our reservoir, properties or characteristics of our flow, or the characteristics of our pressure, right, for a given time. And it's pretty cool in the sense that you're sort of adding this pressure, this parameter time, right, with respect to all your flow concepts in a different way, because it gives you an idea on how to analyze your projects. And this is really important when it comes for modeling and simulation. So moving on. So we have the skin factor. Sorry, 1 second. Let me get my notes. So when it comes to real wells, often near the wellbore, there's some sort of damage or some sort of thing that's impacting the flow or pressure, right? So it's causing this additional pressure drop, and the skin factor is sort of something trying to encapsulate that change or that damage into some sort of value, right? So it's trying to quantify the reduced or additional pressure loss compared to the ideal radial flow. So again, we're always moving from the ideal world to sort of, it's weird, we move from an ideal to a radial to a more practical sense, right? And that's sort of how physicists or mathematicians think, and it's also how petroleum engineers think, right? Is that we start out with a very simple problem. Can we solve it? Can we take a layer deeper and try to solve that? And we continue to do so. So with that in mind, let's talk about the conceptual equation of what the skin factor is and how to solve for it. Lots of these variables you can see, but S is what the skin factor is. It is dimensionless, so now we can sort of try to understand. Again, you go through the dimensions of how you do this, but 2 pi multiplied by the permeability multiplied by the H divided by the volumetric flow rate multiplied by the viscosity, and all of that is multiplied by the change in pressure between the actual and the ideal, right? Because we can always calculate the ideal and we can measure the actual, so these are values that we can really get, and then we can sort of solve for the skin factor. One thing to note is that if it's positive, that means that there's damage. So the skin factor, essentially, that's bad. You want your skin factor to be lower, and if it's lower, then you're actually seeing a stimulation, which means that you're seeing a better flow rate, right? And that sort of makes sense based on the actual minus the ideal, right? Okay, so let's define also, the actual. So the pressure of the actual at the wellbore is measuring the flow at the bottom hole pressure, and the ideal is what theoretically we can calculate by mathematics or by hand, what the pressure should be by the wellbore, right? So again, let's go through some of our assumptions and what this skin factor actually is, right? So the assumptions we're making here is that there's a linear superposition of extra pressure drop due to the skin. So we're sort of assigning accountability to the skin factor in a linear sense, and the same radial flow model is outside the skin region. So when we're looking at the skin itself, we're not really looking at this radial flow model, right? So then for the derivation is that we're basically comparing 2 radial flow pressure profiles, right? So we already know that how to define the radial flow. So if we take the delta of 2 radial flows, in the ideal case is that we kind of get this equation where you have Q is equal to 2 pi kh divided by mu, and you have the natural log of RE over RW. And then when you add the skin, is that you're adding this extra resistance term in your denominator. So in the volumetric flow world, you're adding it to the denominator. So you get this 2 pi kh multiplied by the delta p divided by mu natural log of RE over RW, and you're adding this s. So the natural log of the change in radius plus the skin factor is all multiplied by that mu, right? So, and then if you take that equation and you do the math and you rearrange it all, is that you get the one you see here, where you get this skin factor is equal, and it's this dimensionless, and that sort of makes sense to us, since it is this change in radial flow, and all the values are the same, we haven't added a new parameter, right? So that means the dimensions must remain the same. So then you get this 2 pi kh divided by q mu, all multiplied by the change in pressure, where you do actual minus ideal, and that will tell you. And the reason you do that is to, again, it's this arbitrary indicator of what positive and what negative means. So it allows us to mathematically explain what's damage and what's stimulation, right? So what is the purpose of the skin factor is that it is one of the best indicators or most powerful indicators of our well integrity, right? This is how well our well conditions are. So if you are, and there are these guidelines on what you can say, but you can also use the skin factor to account for near wellbore effects when it comes to pressure and pressure transient testing or well testing. And this is used quite a bit when you're trying to do inflow performance curves, right, in your PTT analysis. And there are guidelines on what we can consider to be extremely bad. So if you see like a skin factor of +5, you can cut your production by almost half. A skin factor by -3 is kind of, you can double your production rate. So that's like almost equivalent to when we're talking about acidization. That's what we should see, right, as that we're doing that. So that's something to take into play, right? Now moving on to the productivity index. This is a very simple equation, but it is a very important equation. And it's relatively simple in derivation as well. But the productivity index, also known as PI, is relating the flow rate to pressure drop, and it's a very practical metric used in production forecasting and well performance. So basically, how many barrels per day for a given pressure. And the equation is J, which is the productivity index, is equal to Q over PR minus PWF, where Q is the volumetric flow rate and PR is the reservoir pressure. And when we talk about reservoir pressure, in reality, you're taking a sort of an average, and the PWF is the wellbore flowing pressure, so the pressure at the well, so of when the fluids are entering, right? So let's go through the assumptions again and the derivation, and finally talk about the key takeaways. So here in this simplistic form of the equation, we are assuming steady state or a pseudo steady state behavior, just for basically generally making a generalization or making the equation more simple. We're again assuming this homogeneous formation, which is generally not the case. And we're assuming it's single phase, which is also generally not the case in real world. But like I said, we are trying to simplify things, right? So the linear relation holds near operating point. So this allows us to simplify the math rather drastically, right? So here we'll show the derivation from radial flow. So before we start, you can think of this like a well with a high productivity index will produce a lot of fluid for a given drawdown or a given scope, right, of pressure. So in our derivation, we start from the steady radial flow formula that we saw with Darcy, right? And we're including our skin factor. So the volumetric flow rate is equal to 2 pi multiplied by the permeability multiplied by the height multiplied by the change in pressure. And that's all divided by mu multiplied by this skin factor added to our natural log change in radius from the reservoir to the well. And we want to we've defined the productivity index as Q over PR minus PWF. So now we kind of now just take that, we're taking Q and plugging it into this equation. And it's relatively simple, right? Is that you see this change in pressure over this change in pressure, it gets canceled out, and you're left with this fraction of 2 pi multiplied by the permeability multiplied by H divided by mu multiplied by this change in natural log of the radius of the reservoir and the well plus the skin factor. So the productivity index is taking into account the parameters we want to look at, right? Permeability, viscosity, geometry, and skin, all into one single value. We're sort of encapsulating that into this index, which is pretty cool because in practice you measure flow rates and pressure, and then you can use that to compute J, which is your productivity index. And if your productivity index J declines over time, your well is getting damaged. And if J jumps after stimulation, then you know you were successful in that job. So if you're hydraulically fracturing, or if you're acidizing, or if you're using some sort of stimulation to improve your production, you should see this increase in J, right? And actually in hydraulic fracturing, you see a humongous increase in J. But then again, so also it's telling us about our secondary and tertiary recovery phases, right, with respect to the well, but it's also kind of telling us about our well integrity. And again, so now this is all valuable information for the entire life cycle of a well. And it's also used a lot for nodal analysis and quick rate estimations, right, when you're trying to explain your reservoir. All right, moving on to this Vogel inflow performance, or also known as the IPR, inflow performance for a given solution gas drive. So the real wells often produce multi-phase fluids. For solution gas drive reservoirs, oil near the well liberated gas causing nonlinear inflow behavior, Vogel's equation is basically trying to capture that in an empirical sense, right? So it's this empirical formula trying to predict the liquid rates as well as unload. And when we look at this equation, it is Q over Q max. We'll define what that is in a second. And E is equal to 1 minus 0.2 multiplied by the pressure at the well bore over the pressure of the reservoir, minus 0.8 multiplied by the same pressure but squared, right? So the variables we're working with here is Q is the oil production rate at bottom hole flowing pressure. Q max is the estimated maximum flow at PWF equals 0. So that's sort of your theoretical Q max, or what you expect through calculation for your flow rate to be. And finally, you have PR, which is the average reservoir pressure, which I believe we've already actually defined. I apologize. But why is this needed? It is basically Darcy's law does not hold directly once you enter the multi-phase world, right? And the multi-phase effects sort of is what dominates near the wellbore. So what this equation is trying to provide is to provide a curve describing the relationship between pressure and flow in a more realistic sense, right? So again, let's go through our assumptions. So the first assumption that this is in fact empirical. So it is, when we say empirical, it is something that's observed, kind of like Darcy's law, or I believe Archie's equation is also empirical. So it means that you basically recorded a lot of different data points to different data sets, and you're analyzing the data, and the pattern recognition or the patterns that come from the data are telling you some sort of equation. And you kind of mathematically denote that pattern through an equation, right? So this was not derived through theorems, basically. So it is empirical, based on multiple data sets for solution gas drive oil wells, right? So that's the context of what we're looking at here. And it is a two-phase flow near the wellbore, which we've kind of made. Again, we went a layer deeper, right? Now we're entering this two-phase flow, and its relation fits typical behavior over a practical range. And now let's go through the origin or the derivation. Since this is an empirical equation, we kind of cannot mathematically explain it necessarily, but we can sort of understand the rationale, the fact that it is derived by curve-fitting production data from many wells. And the way it worked is that Vogel analyzed many fields, and he proposed this quadratic fit to capture the nonlinearity due to the gas liberation and the multi-phase flow near a well. It's not a first principles derivation, so it's present as an empirical curve that maps the boundary conditions to its production. So if you rearrange Q or Q max for measured points, you can solve for Q max from a measured Q. So given the volumetric flow rate and the pressure at the wellbore or at the well, you can sort of rearrange this equation and get your theoretical flow. And that's what it's used for. So essentially, it's a shape-fitting, it's based on shape-fitting curves, right? Based on the data sets for the solution gas drive. And you use this equation, or this inflow performance equation, in nodal analysis, in well modeling, and for predicting the effect of artificial lift, right? So if you're, for your different methods of artificial lift, you want to measure that performance, or the objective, were you able to achieve it or not. And it is entering the mathematical space of nonlinearity, which Darcy is not able to do successfully, right? And again, the most important part, or key takeaway, that it is empirical in its nature, and due to that is that we can, similar to the Archie's equation, is that there are limitations to its applicability, right? Just to the nature, simply when you're using data sets, is that you cannot really extrapolate and make assumptions that for a given environment conditions that it would apply to different environment conditions, right? So that's one thing to note. And finally, from the flow equations, we are going to talk about multi-phase Darcy flow, right? Just because it is really important. So when we're talking about the single phase Darcy flow, it's simply not enough when reservoir generally, or in reality, contain oil, water, and gas simultaneously, right? It's not a single fluid reservoir. So this equation, it gives each phase a reduced effective permeability, and effective permeability, we talked about it in the part 1 of the lecture, and you basically have 3 different flow rates with respect to a given fluid. So you have the new variables. We've seen this equation before, but you're multiplying by this relative permeability of a given fluid in a given phase, right? So now you have this relative permeability, or Kr alpha, and alpha is just depicting however many fluids you have. So if you had, water, gas, and oil, you would have 3 subscripts there, right? And this allows us to think of the permeability, or the Darcy's law, in terms of 3-phase, or 3 fluids, or multi-fluids, or multi-phase, right? And that's what we're trying to do in the end. So why do we need it? It is because the multiple phases share a pore space, and each phase cannot use the entire permeability, right? And this is why we get that effective permeability, or relative permeability definitions. So the pore throats become blocked, and then relative permeability is what really captures that effect mathematically. So how do we go through the derivation? You can basically start with a single phase Darcy flow equation, where your volumetric flow rate is equal to the negative permeability multiplied by the area divided by the viscosity, all multiplied by your pressure gradient. And when you have several phases, the effective permeability to each phase is then reduced, and you can define that effective permeability as a fraction of permeability available for a given phase, alpha, whatever you're looking at, and then you can replace your permeability parameter by the total permeability, or the permeability multiplied by the relative permeability, right? And then you can add the different viscosities for each phase, and you can kind of you have these multiple equations for each relative, or each phase of permeability, or each flow. So this is not really a derivation, but it is this sort of assumption supported by experiments. And again, just due to the fact that Darcy's law is also sort of empirical, so by this nature, this derivation is a step from that. It's based on the assumptions. And the main interpretation that you can take is relative permeability is really essential when it comes to when you're looking at multi-phase flow modeling, when you're looking at water flooding, right, because you're introducing a different fluid, when you're looking at gas injection, because again, you're introducing a different fluid. And it also defines the fractional flows, the shock fronts, and recovery and efficiency, right? And this one you see when you have the relative permeability is that you can measure that due to, we know from core samples and analyzing the different data acquisitions that we take throughout the life cycle of the well, we can take those and then we can create our models, and it can give us fractional flow models and the Buckley-Leverett saturation dynamics, right, which is one of the most important equations, again, for flow movement. So now we've sort of covered a lot of the flow equations, and we'll be moving on to additional equations in a bit. All right, moving on to the Navier-Stokes equation. So it's displayed here. The next 3 equations will be more derivation-like, so we'll just display the equation, the variables, and then jump right into the steps on how to derive it or how to understand it, and then we'll explain why it's important, right? So the Navier-Stokes equation is basically the key concept of this equation is the viscosity, right? But let's try and understand. It's trying to explain how you can deform a liquid as much as possible with respect to a fluid. So it's taking like a force balance and applying it. So think of like F equals ma, but expanded in terms of the density. So if we look at the left-hand side of this equation, we have the rate of change of momentum, which is unsteady and connective acceleration. And then on the right side, it's this pressure gradient, basically a pressure force due to a pressure difference, so this delta pressure, along with the viscous term. so the internal friction, and finally it has the body forces, so gravity or other external forces that are taking into play. So when we look at the variables, we have rho for density, mu for velocity, t for time, and then this function of mu multiplied by the gradient times mu is the connective acceleration term, where it's basically delta v over delta t. You can think of it as that. P is the pressure field. Mu becomes the dynamic viscosity, and the Laplacian velocity, I think we've seen that in the diffusivity equation. And finally, there's some external body forces per unit volume, which is displayed here by the F, right? So let's get into how to understand this equation. So first you start off with Newton's second law, so F equals ma, right, for a given fluid element. So force equals the rate of change of momentum, and you apply this to a small control volume, and this leads to this something called the Cauchy momentum equation. So when you express the forces now, you can do them in terms of pressure. So the pressure force is that negative direction pressure gradient. The viscous force is for the Newtonian fluids proportional to velocity gradients. And finally, you have the force balance, or the body force. And then you want to express the change in momentum, and there you're using a material balance equation, or the material derivative, which is displayed below. And then finally, you can combine them and set them equal to the continuity equation, right, for an incompressible flow. And here we're just sticking to the laws of the conservation of mass, right? So you see this equation just about everywhere in multiple industries, right? Whether you're designing aircrafts or cars, predicting weather and ocean currents, or trying to model flow, right? So even in medicine, so with non-Newtonian fluids, like our blood is non-Newtonian, right? So in the medicine industry, we do have these types of modeling as well that are similar, and actually the petroleum industry took that and applied it to oil and different hydrocarbons because they also behave in a non-Newtonian method. So it's basically the fundamental way of solving in full generality or a general purpose for this like $1 million problem, right? For on how to express the movement of fluid. So it's considered one of the most important equations when you're trying to understand how a fluid is moving with respect to its density or viscosity. So you're taking Newton's laws, you're applying it to fluids, and then you're taking other forces and other parameters such as the pressure and viscosity, and you're combining them together with the conservation of mass to explain the Navier-Stokes equation, right, which is one of the most fundamental equations for fluid mechanics or fluid dynamics. All right, moving on. We have the Leverett J function. Here is also another important equation that you see a lot in reservoir fluids and petroleum engineering. So this is a very powerful concept in when it comes to reservoir engineering, and this function helps us normalize capillary pressure data across different rock types and fluid systems. So what it does is it makes it possible to predict the fluid distribution in reservoirs, and by the end of this derivation, you'll understand why this is important, right? You can already kind of tell based on the variables we're seeing and what it's solving for, why it's extremely important when it comes to reservoir engineering or understanding how your reservoir behaves, right? So let's look at the equation. This J, a function of the water saturation, and it's multiplied by this capillary pressure C divided by sigma, where sigma is this interfacial tension, so the dimensions of that is force per unit length, multiplied by cosine theta, a trigonometric function, multiplied by the square root of permeability over porosity, right? So our variables variables we're pretty familiar with. So let's get into the derivation. So we start off with our capillary pressure, right? And we're trying to know what the non-wetting versus wetting pressure is. And once we do that, is that we can apply our dimensional analysis or understanding how the equation behaves depending on the dimensionality of it. But the Leverett function basically assumes that the pore media behave like bundles of capillary tubes, right? We said that in our reservoir, we like to think of it as this complex capillary system where you kind of have channels and pores. And the capillary pressure depends on the interfacial tension, the contact angle, and the mean pore radius, which is telling us more about the porosity and the permeability, right? And what they're doing is they're normalizing the equation by removing the rock and fluid properties with this cosine theta parameter here. And they're introducing this characteristic length, which is the square root of permeability over porosity, right? Because, like we said, permeability, when you look at it dimensionless, we want is some sort of length squared, so you divide the square root of it, you just get some length, right? And when you combine the terms, the dimensions, they become the final equation that you get, right? Which is, you get this Leverett function that's a function of water saturation, and it's relating the capillary pressure and permeability and porosity, right? So this helps us normalize our capillary pressure data, and it's making assumptions about pore geometry, but it's allowing us to kind of manipulate, like we said in the previous lectures, is that when you have dimensionless parameters, it allows you to work with them and use them interchangeably in different equations to help understand or explain other things, right? So this is one of the most important functions, and you see a lot of it in reservoir characterization and reservoir simulation. Now let's move on to our final equation that we'll be talking about today, which is the Buckley-Leverett function. So the Buckley-Leverett function, it's again one of the most important equations in reservoir engineering, and this theory predicts how one fluid is able to displace another. So if we're looking at water displacing oil in a given porous medium. So it's used a lot when you're trying to look at reservoir engineering concepts or reservoir engineering approaches, such as water flooding or enhanced oil recovery. So the different ways we can use it in a secondary and our tertiary phases. A reservoir engineer would use this equation a lot to try and understand how to apply certain methods for improving production, right? So first, let's go through the equation. This delta S over delta T, as you can see, is the water saturation derivative with respect to time, and you're adding it to what looks like something similar to Darcy's law, but it's like this flow rate divided by porosity multiplied by an area, and that's all multiplied by this gradient of fractional flow with respect to a given distance, right? Where FW is the fractional flow of water, A is the cross-sectional area, phi is porosity, Q is the total flow rate, and T is time, and water saturation is depicted by SW, right? And when we want to understand what FW is, because we're going to be taking the derivative of it, right, mathematically. So when we want to understand fractional flow in terms of water saturation, you get these this lambda function. So you have lambda W over lambda W plus lambda N, and you can expand that to be using relative permeability functions. So the relative permeability of water with respect to the viscosity of water over the relative permeability, basically taking a fraction, right? The relative permeability of water plus the relative permeability of some other fluids. So here N, but it could be water or gas or so forth, right? Where KRW and KRN is the relative permeability of water and oil, and your viscosities is mu W and mu N, okay? So let's go through the steps of derivation. So first of all is that you want to start again with the mass of conservation, the law of conservation of mass. So you're kind of setting your equation equal to 0 to get that balance. And what you're doing is you're putting in what we were talking about, something that looks like Darcy's law for each phase. So the relative or the multi-phase Darcy flow equations that we talked about. And when you enter that, you have a flow rate for water and a flow rate for oil with its relative permeability or effective permeability, you can say, and then you want to define the fractional flow, which we just defined previously, but it's also is either QW over QT or Q oil over QT, but you're basically taking the fraction of a certain fluid, applying the equation, and you know that lambda here is the mobility, what we defined earlier in Darcy, which is basically your K over mu, but here it's with respect to a specific fluid. And finally, when you combine the terms, you get this expressed total equation for Qt, and you can substitute it again into the conservation of mass equation. So you can solve this equation for water, then for oil, and you finally have the total flow rate, and you can sort of solve the final equation balance, right? And this is really important for, again, predicting how water moves through a given reservoir or porous medium over a specific time, or if you're going to start water injecting. So if you're designing a water flooding project, this will tell you how the flow of that water behaves and how you can improve either the flow rate or the overall production. And this allows you, since you can connect it to the total flow rate, and you know the water flow rate, is that it allows you to estimate your oil recovery and define the efficiency to how you're recovering your oil, right? So it is something very simple. It's kind of combining the previous equations that we've had or we've seen in the past and putting them together to understand how we can manipulate our reservoir and understand how we can simulate our reservoir or simulate our production. So this is where reservoir simulation, this is used a lot. You'll see it as an equation that you can model around. So it's very important to modeling. And it's also important on trying to understand how you can manipulate basically the water within your reservoir or water injection to manipulate your overall production, right? So the equation, the Buckley-Leverett equation, is it models the immiscible displacement. So it's talking about the displacement of fluid in a given porous medium, and you're generally displacing that fluid or your hydrocarbons with water, right? So that's something to keep in mind. And it's again derived, like most things in physics, on either the conservation of mass or the conservation of energy. But here they're using the conservation of mass equation, and they're just putting it in the form of a Darcy's law equation, a multi-phase flow of Darcy's equations, which helps you optimize the recovery strategies in oil reservoirs. So that covers the Buckley-Leverett function. So, for the majority of this lecture, I'll go over the conclusion basically on what we talked about. So, in conclusion is that petroleum engineering is something still very relevant, still very important to learn. As a petroleum engineer, you're solving lots of problems. There are lots of still unknowns in this world, in the industry, and with all the movements towards renewable energy, is that for the non-renewable energy, it is becoming more and more critical to do things in an efficient manner and an optimal manner. So companies are really looking towards maximizing or optimizing their methods, right? So there's a lot of unknowns. So there's lots of problems out there that still need to be solved with respect to the petroleum engineering industry. And also, like I said, lots of the petroleum methods or mechanics or how to solve problems are becoming or proving to be the way that you will solve a problem in the renewable world. So lots of the oil and gas industry companies are taking the lead towards that energy transition, which as an industry, people are aware of that, right? So as a petroleum engineer, your problem-solving skills and your knowledge of how to handle unconventional and conventional oil reservoirs, no matter the field or subfield that you do join, this is a really relevant field and will continue to be important for the next few decades, at least we can say, and will continue to be important, especially when the energy transition really starts to kick off, right? So with that in mind, we're going to recap what we've talked about, and this is everything we've talked about so far. And I think to conclude on this, as the last part of the lecture will just be a small discussion on more modern topics. So, for example, like how artificial intelligence is being applied to the oil and gas industry and etc. But to conclude what we talked about with respect to the petroleum engineering is that we gave an introduction on how on what petroleum engineering was, what are hydrocarbons, where do they come from, why is it relevant to know where they're coming from, how do we get them, and what are the skill sets that a petroleum engineer would need to know. And from there, we went on to define some terms and topics that are essential to all petroleum engineering topics or classes, which are basically the petrophysical terms, which is the rock properties and the fluid properties that a petroleum engineer must know. And then after that, we talked about the life cycle of a well. So we started at the very beginning with exploration and what are the mechanisms or methods that we use for exploration. And then once we've identified our prospects, we moved into the next category, which is the drilling. And then within that, we talked about the subcategories of drilling and what are the different types of drilling engineers. So the fluid engineers, the pressure fluid engineers, the directional drillers, and also the drilling engineers that are logging, right? So acquiring data as well and using that data to optimize their drilling patterns. We also talked about how the evolution of the technology has really impacted on how well we drill and how we can increase that surface area exposure to our reservoir, which is basically increasing the overall production for a given single well, right? Which is making us more money. And once we've drilled our well, no matter what the shape is, we talked about logging and how a wireline engineer would go in and put their tools down and basically acquire different data. And that's here where we're really defining and drawing out what our reservoir and our rocks look like. And we're understanding the true nature of our reservoir in more detail, right? And we're using pretty cool technologies such as nuclear magnetic radiation. We're using Einstein's photoelectric effect. We're using sonic tools. We're using lots of cool technology to be able to measure the permeability and porosity. There we also discussed about Archie's equation and why it's so important, even though it's an idealistic world, right? And we touched on how that equation helps us relate resistivity to water saturation. And we talked about other ways of measuring the porosity, permeability, right? The indicators that we can use to measure these things as a wireline engineer and how we can transfer them to log charts, right? And then we talked about the completion engineers, and that's a subfield that sort of exists throughout different steps of the reservoir. And we talked about why that was extremely important, and that also had its subfields on when you complete a well, or whether it comes to the casing or cementing, and how it's iterative and it's sort of incrementally done. And then we moved on to more reservoir-based jobs like production engineers and reservoir engineers, and we talked about the different types of enhancement recoveries that a production engineer would do, such as like we talked about the primary phase, the secondary phase, and the tertiary phase, and how a production engineer could switch a well to water flooding or infill drilling. We talked about how artificial lift or stimulation can be done. So we talked about hydraulic fracturing. And We also talked about acid stimulation and how we're really improving that productivity index, right, when we're using these things. And we explained the concepts behind each one. And we talked about CO2 recovery, enhanced oil recovery, same thing, but just basically the different methods that a production engineer will do to improve the overall recovery, and the different metrics or data points that he or she would need, right? And then we move to finally the reservoir engineering, which is kind of like the strategy thinking, the analytical engineer that is sort of making the game plan from start to finish, running the different simulation models, understanding how different scenarios can impact different outcomes, and trying to choose the most optimal plan for a given reservoir over a period of time. We talked about how this continuously changes and the methods that a reservoir engineer would use or need to use to be able to pick the most optimal way. And we kind of brought in this money parameter with the reservoir engineer, which really tied greatly into the next subject, which was the petroleum economics. And petroleum economics, here we talked about how to define a project, how to define capital expenditures, operational expenditures, the different risks and uncertainties throughout the different stages of a given project, and how external factors within a project become a huge influence and become very important for oil companies to be aware of, whether it's political or geopolitical situations that they have to know about, right? And then within each country, they follow their own rules and they have their own regulations and policies, which also come and have an impact on the oil reservoirs. We also discussed and defined what a proven reserve was versus a reserve, and why it is really important to classify that to be able to produce a well or start a project. We talked about financial terms such as rate of return or productivity index or performance flow index, and these different project terms that are financially related that are telling you how well or how bad your project is doing, and the risk and the uncertainty associated with that, and how to manage through a given project with these parameters. And then after that, we sort of concluded the part one, and we moved on to part two, where we took lots of the concepts that we saw from a high level or from a discussion perspective in part one, and we took a layer deeper by explaining those mathematical equations or those physics-driven equations, right? And the way we did that is first we explained sorts of the fundamental mathematical concepts that people should be aware of or are used quite frequently in petroleum engineering. And then we took those fundamental equations or fundamental theorems and we expanded them to the application of petroleum engineering equations. And they're mostly flow equations, but we talked about some fundamental physics concepts like the conservation of mass and the conservation of energy, and explain how those play an important role. And then we talked about multiple different flow equations, where we started out with the basic form of that equation, like as Darcy's law. We took it to a radial front, where we're explaining the flow in terms of a radial movement to sort of come closer to the well-like structure. And then we took a deep layer and made it, multi-phase. So we're accounting for the different fluids. And we did that with multiple different types of equations. And we finalized with some reservoir engineering principles and functions that are really important for characterizing water and oil.